Today's session is brought to you by API Engineering. The topic is for the webinar is HVAC design insights for off-road vehicles. Before getting to the webinar, I would like to introduce about speakers today and will share a brief introduction about APA. Yeah, myself Bharat, as a project manager and working in mechanical engineering design and HVAC design and simulation with 15 plus years of experience. And joining with me for this today's webinar, Mr. Michael Geiger from Germany and 20 plus years of experience in thermal management and in the various domains like mobility and energy sector. I'm glad to introduce APA Engineering, a 25 years old organization with over 500 employees, and we are headquartered in Chennai, India, and serving clients in the US, Canada, Germany, Netherlands, and Australia. We are ISO 9001 certified for quality, ISO 27000 certified for information security, and we have a HVAC certified, it's ensuring the high data protection. So our expertise spans 4 divisions: engineering, sourcing, compliance, and technology. In the sourcing, we support the clients with right from the supplier identification and doing the audits, inspections, and logistics and the deliverable. So compliance provide software and services for the global chemical compliance, material compliance, including the conflict minerals such as IMDS, REACH rules, and Prop 65. In technology side, we develop custom IT products and serves to enhance the enterprise productivity. Now let's take a closer look at our engineering division. We are a 70 members strong team of mechanical, electrical, and electronic engineers working as an extended design partner for clients across the industries such as automotive, oil and gas, special purpose machinery, medical, and plant engineering. So we have 5 core verticals that you can see: product engineering, manufacturing engineering, and plant engineering, digital modeling, and embedded engineering. At AP Engineering, the product engineering transforms concepts into a high performance. For example, we are today in HVAC. So all the HVAC we can see from 3D modeling and the manufacturing things to visualize the design and prepare for the production. So right from the concept design to the manufacturing design. If some parts, if we do any reverse engineering or re-engineering to improve the existing solutions and also do some benchmarking design. For virtual validation, we do stress, stiffness, fatigue, and vibration simulation to ensure the durability, especially for off-road vehicles. And CFD and thermal solution, of course, for optimize the airflow, heat transfer, and the cabin comfort. So weight optimization to improve the efficiency. And alternate materials such as for durability, corrosion resistance, and cost effectiveness, we do it based on the requirement. We do the alternate material selection and material design. Together, these steps ensure the HVAC systems are robust, efficient, and tailored to the demanding needs of the off-road vehicles. So coming to manufacturing engineering, streamlining the production with the resource optimization, layout design, tooling, picture design, CNC programming, and PPAP documentation. So coming to plant engineering, of course, providing the intelligent building information modeling, including HVAC duct routing, equipment layout, electrical design, drafting, and structural modeling and 2D detailing, and the piping modeling. So digital modeling nowadays, many more for the marketing tools. We support like creating precise 2D sketches, realistic 3D renderings, engaging the animations, and comprehensive technical documentation. So embedded engineering, along with our partner, we do services for PCB design, signal power electronics, and the embedded UI UX and AI and ML applications. Let's get and dive into today's exciting session on HVAC solution for off-road vehicles. Here is the agenda for today's webinar. We'll begin with the introduction to HVAC. Next, we will explore how the refrigeration cycle works and break down the key system of the components. Then we'll discuss the three main challenges in off-road vehicle. Following that, we'll walk through a live demonstration of heat exchanger sizing. Also, we'll cover the refrigerants and updates, looking at the latest developments in the refrigerants, including new regulations, technologies, the trend shaping in the industry. Finally, we'll have a Q&A session to address all your questions and insights. Okay, let's get started with our first topic, introduction to HVAC. I would like to invite Mr. Michael Geiger to take over, and yeah, over to you, Michael.
Thank you, Bharat, for the introduction, and hello, and also warm welcome from my side. Yes, I want to give you a short introduction about HVAC. So what means HVAC? So HVAC means heating, ventilation, and air conditioning. That means we always under very cold, very warm conditions. We need to make sure that the driver feels always comfortable. And of course, we also need to provide a specific amount of fresh and filtered air from the ambient. So here we need to make sure that we minimum provide 43 cubic meter per hour into the cabin. And of course, you know the HVAC system from a vehicle, from a car, but for the off-road applications, we have some special requirements because we are working under really harsh environments, harsh conditions. So like dust, we have extreme heat, vibrations, and under these conditions, we need to make sure that the HVAC system is working properly. So on the next slide, I will give you a short introduction into the refrigerant circle. So here you can see that's a log pH diagram. On the x-axis, we have the enthalpy, so that's the inner energy of the refrigerant. And on the y-axis, you can see the pressure. On the left-hand side in this area, we have subcooled liquid. Inside here, this area, we have the mixed region between liquid and vapor. And on the right-hand side in this area, we have superheated vapor. So here we have only gas. So we are starting at point 1. At point 1, it's the inlet to the evaporator. The evaporator we are using to cool down the air. So that means we are reducing the pressure by using the expansion valve. So if we reduce the pressure, we also reduce the temperature. So that means we can reduce the pressure in a way that the temperature of the refrigerant is below the air temperature. And so we can transfer the heat from the air to the refrigerant and cool down the air. That means we are heating up the refrigerant from point 1 to point 2, and we are cooling down the air. From point 2 to point 3, we are using the compressor to increase the pressure on the refrigerant side. It means if we increase the pressure, we also increase the temperature. And because here on the evaporator, we transfer the heat from the air to the refrigerant, and our target on the condenser between 3 to 4 is to transfer the heat from the refrigerant to the ambient. And therefore, we need to increase the pressure, so in the way that the temperature is higher compared to the ambient, so that we can transfer the heat to the ambient. And then, of course, after transferring the heat to the ambient, then we have to go down using the expansion valve from the high pressure to the low pressure, and the cycle is starting from beginning. So the short summary, that means from 1 to 2, we have low pressure, low temperature, so we can cool down the air, which is entering into the cabin. Then we use the compressor to increase the pressure. We increase pressure and temperature so that we can transfer the heat from the refrigerant to the air, to the ambient, and then we go down with the expansion valve again to the low pressure side. So that's a short introduction to the refrigerant circle. And on the next slide, I want to show you how this system can look like. Here on the right-hand side, you can see a HVAC unit. This unit is installed inside the vehicle. So that means here we have an evaporator and with the fan. So from that we go, as I already told, from the evaporator to the compressor. We increase the pressure and the temperature to the condenser. We check the heat and then go back via the expansion valve to the evaporator. So inside the HVAC or inside the cabin, we have such a HVAC box. This example, we have a housing, we have the evaporator, there is a blower, then we have, in this case, it's for electrical vehicle, we have a PTC heater, and from the PTC heater, we go via the ducting inside of the cabin. Yeah, so what are the three main challenges in the off-road HVAC? So for us, these are three main topics. One, of course, is the performance. So that means we have to meet the performance for cooling and heating under extreme conditions and within a really limited space claim. So that means we really need to pull down the heat during summer inside the cabin, heat up the cabin or defrost the windshields. And of course, this needs to happen with minimum power. So this means energy efficiency must be as high as possible, especially then for electrical vehicles. Then the second topic is robustness. So we have to withstand high requirements for shock, vibration. We have a lot of dust, harsh environments. Temperatures are really wide range of temperature from -40 to 50 degrees. And of course, we also need to make sure that we are corrosion resistant for really a long durability. The third point for us is always the cost effectiveness. So that means usually compared to on-road applications, automotive, they have high volume and also high engineering cost. But here we have really, most of the time, really low volume projects where we also need to optimize the material, of course, optimize the design of the HVAC. It's really a cost-driven design. We need to make it modular, service-friendly, of course, and we need also to find the right balance between the engineering cost and between the life cycle cost. That's a short overview about the key points, and I want to hand over now to Bharat, and he will give you some more details.
Thank you, Michael, for the great insight about brief HVAC system and the main challenges. In the continuation of Michael's points, I want to elaborate more on these three challenges. So, when it comes to performance, normally when we talk about HVAC design for the off-road vehicles, the first priority is thermal comfort. Hope you are all aware these machines are mainly working in the different environments and different climates. Like for example, for winters it goes -40 degrees Celsius. For summers it goes +50 degrees Celsius. So this system not only maintain the stable cabin temperature, okay, but also delivers the fast cool down cooling in the hot conditions and also a rapid warm up during the cold conditions. And importantly, we cannot forget the defrosting and defogging because it's a safety. Clear visibility is required for safety drive. In off-road environments, like if you see in construction sites, some mining area, the forest side and the agriculture fields, the operators always face some difficulties. Suddenly the rapid temperature changes and high humidity, and also some environments very dusty and particularly some dirty environment. These conditions can cause fogging on the inside the cabin and also frost or condensation on the outside of the cabin windows. So another important factor is air quality. For off-road vehicles, oftenly, as mentioned earlier, the dusty and smoky, even some hazardous also. That's why cabin pressurization is essential. It keeps the dust and fumes from entering the cabin. In addition, we have to use the high efficiency filters because, to capture all the fine particles to stop outside. It should not go inside the cabin. And also when we are designing, the filters needs regular replacements. The filter housing must be designed in such a way that easy for servicing ensuring the minimal downtime in the field. So next come to the airflow. Airflow distribution. Comfort is not just about the temperature. It's also about how the air is delivered into the cabin. See, our goal is to provide the uniform airflow throughout the cabin with well-balanced zones. For example, if you see the, I can see the right-hand side CFD simulation of the truck cabin, the always warm air at the feet. We should maintain the warm air at the feet and cooler air around the head. So this way that this system, so we need to provide a proper adjustable vents and the proper blower speed controls. It gives the operators flexibility to fine-tune their comfort to suit their needs. And as coming to system efficiency, see, efficiency plays a major role, especially when engine power is limited. The HVAC system needs to be designed with optimized compressor and evaporator sizing, so it delivers the maximum performance and within the minimum load. So now I will walk through here such a evaporator which used in the off-road vehicle. By using we have a specialized software called Coil Designer. So to meet the target performance and also sizing the component within the compact space. So I'll go to the software. So here is the Coil Designer software. It's a GUI interface of the software. Since due to the time constraint, I already applied the boundary conditions of and the parameters. So I'll quickly go through the parameters. For example, the tubes. So when we meet now I'm going to run for 6 kilowatt cooling performance for the off-road evaporator, off-road vehicle evaporator coil. So in tube configurations, there is a different types of configuration, and also the number of banks and tubes. It plays a major role to achieve the performance target. So here, based on our application to meet the 6 kilowatt target performance, we choose the tubes, 8 tubes per bank, and number of banks is 4. If you see the column, it's a bank column as a 4 columns. It's called as a bank, which is 4 banks, and 8 rows. That is the tubes per bank. And also very important that the airflow should always cross flow with the refrigerant. If you see the air coming this side, and our refrigerant inlet should be in the opposite side. The circuit we have to design such a way that it should not reverse flow. Always should be positive towards against the air. So then only we can meet the better performance on the results and also to meet the target. And on off-road vehicle, we have a very limited space. So we need to design the evaporative coil within the limits of the space available. So the target length is 350 mm, and also we choose the copper tube outer diameter is 9.52 with a 3/8, and thickness is a 0.81 because it's working on the off-road and very vibration and sound. So we have to choose the proper thickness of the tube, and these are all the spacing. And the fin types, if you see the fin types, minimum it should be maintained 1.8 mm to de-icing, so the water should properly drain from the evaporator. So that's how at least we need to maintain 13 fins per inch, and thickness is 0.14. And refrigerant we use for this R134A, and based on the heat transfer and pressure drop correlation, based on the standards we have chosen. And also another inlet boundary condition, we have to give the inlet temperature to the temperature, and also the relative humidity factor, and the actual flow rate from the customer side, what the blower speed or actual fan speed they have provided, that input we need to provide here. And also the refrigerant side, the temperature, evaporator temperature 0 degree, and quality mass fraction 0.22. If we don't get any values, then we can using log pH diagram we can use. And also we are based on the experience, we use this value and the mass flow rate also. So I'll quickly run the simulation. It will actually give the fast solution. You can see our total heat load 6.6 kilowatt, but our target is 6 kilowatt. So we reach the target value of cooling performance 6.6, and also the superheat is nearly 5 Kelvin, and the refrigerant pressure of 0.2 bar. So I'll quickly go to the 3D view how our coil design. We designed the coil. You can see the 3D view of it, and you can see the air dry bulb temperature, the heat tube, how the air temperature inflows. And also we can see the refrigerant pressure on the each tubes. You can see. And also we can able to see the refrigerant temperature on how the superheat the trikelvin we achieve. We can able to see this. And we can plot the whatever the value that we can give the plot diagrams for the heat loads in the tubes and how the layout of the circuit we have provided. Everything we will get it from the in this results. So quickly I'll run the export the summary of the result. So here we can get the size of the heat exchanger. So 350 mm width and height 203 and the depth is 78 mm. So as per our required sizing within the limited available space, we designed the coil, and also we achieved the target performance of 6 kilowatt and the saturation delta superheat is 5 Kelvin. So these are the typical results of the evaporation simulation. See, we received the input from the coil designer, and this is a different type of evaporator. And we can able to create the proper how looks like in the real world of the evaporator. We can provide the 3D model and also with the expansion wall connection. So I'll quickly run the simulation results. How the heat loads on the each tubes, and also air temperature in the flow of the air temperature in the different region. And as shown already in the refrigerant temperature, pressure, and dry bulb temperature. Okay. So next, robustness. As Michael said, the off-road vehicles operate in very robust terrains, which means the HVAC system is constantly exposed to vibration and shocks. To ensure the reliability, we use the durable mounting methods and anti-vibration designs. On top of that, we do FEA validation to meet the proper mounting to withstand the components without any failures. Another challenge is dust and mud ingress. To address this, we use the sealed filters and IP-rated enclosures to protect the sensitive components. For example, most of these off-road vehicles, the contents are outside. So because of the environment, we need to choose the proper coils for the condenser. For example, we use the micro-channel coils or round pin and tube coils based on the environment and also the serviceability also very important. And temperature, as already we discussed, the minus 40 degrees Celsius to plus 50 degrees Celsius. Every component that must be tested and validated across the wide operating range. The corrosion resistance is very important. Since these vehicles are exposed to rain, mud, even the salty environments, the corrosions definitely some corrosion will be there. So we have to resistance that by choosing the proper material. We have to using the anti-rust coatings and carefully selecting the materials like aluminum or copper alloys that can endure the long-term exposure. Yeah, the space constraint that is one of the toughest design challenges in the packaging. Off-road vehicles, we have very limited space available to design such a HVAC system. Maybe under the space available only under the seat or around the cabin. So the system has to be more compact and modular, and also it should be efficient. Cost effectiveness is the key in off-road vehicle design, where the durability and performance are essential. And also that's why we use always a modular assembly to simplify the maintenance and reduce the downtime. It means if any parts got damaged or any faulty happens, it should be quickly replaceable instead of changing the entire unit. So particular part alone, like a Lego toy, So if anything is spoiled, we can fix it immediately. So in such a way that we have to design and optimal material selection like aluminum alloys, balanced strength and weight and cost side, of course. While standardize the components, we have to simplify the sourcing and cost, lower inventory costs. That's also play the main role. And durability side, as we do FEA and CFD validation, we ensure the durability and reducing the life cycle costs. So housing is like another key factor, as Michael said, the off-road vehicle compared to on-road vehicle, very less volume of production per year. So we can suggest like if a very low volume production, we can go with sheet metal housing. If the medium volume production they use, we can suggest for vacuum forming, and high volume we go with for the injection mold designs. So these are all the strategies deliver a robust, efficient system within the budget. So next, Michael will cover up the refrigerants. Over to you, Michael.
Okay, thank you, Bharat. So I want to give you a brief overview about the refrigerants and want to start with the history of the refrigerants. So in the past, we were using natural refrigerants like propane and CO2. And in 1930s, we started with using chemical refrigerants, so the CFCs. One example is R12. But then we became aware that this refrigerant is damaging the ozone layer. So that means it has ODP, ozone depletion potential, of 1. So that was the reason why in the 1990s, we had a transfer from these CFCs to the HFCs, a new kind of refrigerants. So there we introduced R134A, which has no harm on the ozone layer. But this refrigerant has a really high global warming potential. So that's a GWP, global warming potential, and that's about 1,430. So that means R134A has 1,430 times higher impact on the global warming compared to CO2. And as we need to reduce global warming, and then in 1913, the HFOs, so refrigerants, have to be introduced. And one example is R1234A, which you can find mainly also on automotive applications. So this one has a really low GWP, about 4. So it's no harm to the ozone layer and a low GWP. So that's quite good. But in the meantime, we can see that here we have some issues with the TFAs. TFAs, these are chemicals who stay quite long time in the environment for hundreds of years. And in the meantime, you can find these TFAs in the environment, in the human body. So there is also a need to reduce these TFAs to protect the health of the people. And therefore there is this new PFAS chemical concerns we have right now, and this new PFAS regulation. And they are looking for new refrigerants, and these new refrigerants might be the natural refrigerants like used in the past. So there we have at the moment 2 main alternatives. One is R290 and the other one is R744. I can show you some comparison about the refrigerants on the next slide. Here you can see the comparison. We have here the different refrigerants, 134A, 1234YF. So they are quite similar. 1234YF has lower performance compared to 134A. Is a bit more flammable compared to 134A, so it's in the category of A to L. And but can be used more or less with the same refrigerant systems compared to 134A. If we go to the natural ones, we can use R744 CO2. That's really different because there we have really high pressure levels compared to the standard ones. So here the pressure can easily go up to 130 bars. So that means also new components have to be developed if you want to use CO2 as a refrigerant. Of course, it's not flammable, but it's quite positive and has also a low impact on global warming. The second alternative we have is R290, that's propane. So propane has more or less similar pressure levels compared to the refrigerants we are using today. Has also really a high performance at low temperature and also good performance at high temperatures. But the issue, of course, propane is highly flammable. So that means that the refrigerant circuit needs to look different. So there we have indirect systems. So we do not go directly with propane inside the cabin. So there we have to cool down water and then go with water or coolant inside the cabin for cooling the air. So that means the complexity of the coolant side will be higher. But anyway, R290 is from the refrigerant the behaviors and from the thermodynamics, a really, really good refrigerant. Okay, so on next slide, we want to give you a short overview about the different regions in the world. So that's our impression, what we have. And so in Europe, we can see on the automotive, the transition is completely done to R123for YF. And some vehicles already use R744, but just a low number of vehicles. On mobile machinery, we see that R134A is still in use, but there is a transition to R123for YF. So most of the new projects we see R123for YF, not in all, but most of them. And we are expecting these new PFAS regulations where these TFAs will be banned, and that would lead to the need of using new alternative refrigerants. And there we have these two alternatives I already explained with propane and CO2. In the US, on the automotive side, also R34A is banned from 2022. So also R123for YF is widely used. On the mobile machinery, we also see there still R134A on the machines, but also transition to YF. And also in the US, they also want to go to alternative refrigerants. So, for example, Ford has applied to register R290 as a refrigerant, for example. In Asia, we see automotive. There's still R134A is still common, but there are also YF the use is also growing, and there's also a target to reduce refrigerants with lower GWP below 150. Maybe you remember R123for YF has a GW of higher than 1,400. On mobile machinery, we still, of course, 134A is still common, but we also see their projects with YF at the moment. So that's a rough overview about the different refrigerants from our point of view.
Yeah, thank you, Mike. Thank you, Michael, for explaining the great difference between the refrigerants and the comparisons. So, and next, the summary of the HVAC and thermal management system. So, as for engineering, we can, we have, as I mentioned, 20 plus years of experience with, in the domain. So, right from the concept development till the HVAC, finalizing the complete HVAC design, and by using the virtual validation like FEA and CFD simulations for the cabin, for thermal comfort, the airflow, And for the wherever we're using the plastic housing, we can do the plastic design and mold flow simulations. And of course, the citing the right components to meet the exact performance target. So we using the Coil Designer, to as we went through a demo. And we have a website where you can get the entire refrigeration system level of simulation. You get the performance of the entire system level. And we can have a separate session for this to give the more insight about Coil Designer and website. And not only for HVAC, we can able to support the design until the duct. So even the ducting design by using the blow molding, and also the passenger comfort for using the CFD cabin analysis. And we do the manufacturing drawing. And we have, as I mentioned, we have the sourcing division. We can source all kind of parts, HVAC related parts from India. So with we can bring the faster way, and also the great support from our sourcing division. So we are now open for questions. Please use the comment box or email us. The email ID mentioned, engineering@oppoengineering.com. We would like to hear your thoughts and others, any queries. So let's wait for some queries. You can use the chat box. Yeah, we got a couple of questions. So how fast how fast does the cabin cool down, and to what temperature? Michael,
Yes.
Question from.
Yeah, usually as a minimum requirement, we want to meet the ISO standard 10263. That's a standard for mobile machinery. So there we have to cool down the cabin from 38 degrees Celsius to 20 degrees Celsius in minimum 15 minutes. But we see on most custom requirements the temperature, ambient temperature is higher. It's not 38 degrees C. Usually it's up to 45 degrees C. So that means from 45 degrees C, we have to cool down to 20 degrees C, and that should happen in less than 15 minutes.
Thank you, Michael. The next one, what refrigerants will be used in the future for mobile applications?
Yeah, that's hard to answer. Hopefully it will be the natural refrigerants with CO2 and propane. Both has pro and cons, as you have seen. So with R744, the pressure level is really high. So therefore also a new design of the components is needed. So also engineering effort is quite high. And on R290 we have similar pressure levels compared to the refrigerants we are using today. But of course, due to the flammability, we need to minimize the risk, develop new systems with a minimum refrigerant charge, having indirect systems. So both has pros and cons. I personally believe that R290, I think, fit better to mobile machinery, we can use similar components like we have today. And we have also very high performance at low and high temperatures.
So I thought, So thank you, Michael, for your valuable insights on HVAC design and also some of the refrigerants correlations that you have shared, and also for answering all the questions. And we have we received a few questions that we will reply to email. We'll answer for you that. Yeah, now. We are at the end of the session. Vote of thanks. So on behalf of everyone at AP Engineering, thank you for joining today's webinar. We hope you found it insightful and very useful for the better understanding of how HVAC and the off-road vehicles and what are the main challenges that we are facing and the component sizing. So hope you all have a great insight on that. You will soon receive a short survey about this webinar. We would appreciate your feedback and suggestion. It will be help us to improve on future webinars. Thank you again for your time and participation. It's truly inspires us to keep sharing the knowledge in the matters. And finally, and remember the great design is not just about engineering, it's about creating the solution that endure in the toughest conditions. Thank you, Michael.
Yep. Thank you.
Okay.
Goodbye.
Thank you all. Thank you. Bye. Thank you once again for everyone joining the session. We'll catch you up in the next webinar.